Any questions about anything?
I do have a question. So, how much work should we show for the one-to-one onto map for the exam?
Oh, the conformal mapping? If you show how you can break down the mapping for the conformal mapping question on exam 2 by showing it's a composition of sort of basic maps. Getting the basic if those maps are correct, then of course you'll get the points. But if you somehow make minor errors, the only way we can tell where you made your minor errors is to write down your work. But basically getting the right sequence of maps is the key.
Yeah, I was just wondering if you had wanted us to actually show that they're all one-to-one, but if they're all basic building blocks, that's fine.
Well, you can use facts that are in the book or that you know. Other questions? Let's see, this is a wonderful highlight of the course, is that we can show now that we have the Poisson integral formula and the Schwartz theorem about solving the Dirichlet problem. We can show this famous fact that if a continuous function satisfies the averaging property, then it's actually harmonic, which is kind of a mind-blowing thing. We only assume it's continuous, but of course harmonic functions are infinitely differentiable and satisfy the Laplace equation. And so it's a very strong consequence. And you think of the averaging property, it's kind of a believable property, that some physical problem that's about diffusion, like temperature diffusion, is likely to satisfy an averaging property. I mean, in the steady state temperature in this room, the temperature right here is the average in a disk around it. So naturally, temperatures, you believe, could satisfy the averaging property. Of course, to prove the averaging property, we know that the temperature is harmonic, and you use the famous Green's formulas to get the averaging property. But it's an if and only if fact, which is pretty interesting. So the proof is going to be easy, and it's going to be the first time I use this standard trick. Let's see, being harmonic is a purely local question. So I can restrict attention to a disk. So I can restrict attention to a disk, and in fact, a disk in omega, and by doing a change of variables, let's make the disk in omega. How about dr z naught closure contained in omega? So I have a function that's continuous up to the boundary and satisfies the averaging property inside that disk. And now I can do a change of variables to move that disk to the unit disk. So I do an f of z equals z minus z naught would move z naught to the origin, and dividing by r would make it the unit disk. So now I have a function. Now I'm going to study the problem on the unit disk. So we can assume we're doing, we can reduce the problem to can reduce our attention further just to the unit disk. So what do I have? I have a function that's continuous up to the boundary, unit circle, and satisfies the averaging property inside. And the classic trick is, if you want to show something's harmonic, well, you take the Poisson integral of its boundary values. So this is a classic trick. Let's let u twiddle of z be the Poisson integral of the boundary values of u. So let's see the Poisson integral. I think last time I wrote out this formula, I didn't have the square in the denominator of the Poisson integral. Well, I fixed that in the notes. Okay, so that's the Poisson integral of the boundary values of the little u. Call that a u twiddle. We know that u twiddle is harmonic on the inside. Let's see, we know it's continuous on the closure. It extends at least to be continuous on the closure. And harmonic on the inside. And it has the same boundary values as u twiddle. So that would be on the unit circle. And now here's a fascinating thing. Harmonic functions also satisfies the averaging property. And so here I've got a u twiddle. If I take u twiddle minus u, so here's the aha moment. U satisfies the averaging property too. And so why don't I take u twiddle minus u? U twiddle minus u satisfies the averaging property. And remember, so here's the idea. The averaging property implied the maximum principle. So here's the idea. The averaging property implies the maximum principle, and that u twiddle minus u is 0 on the boundary. So if there's a maximum principle, then u twiddle minus u is less than or equal to 0. So the idea is that the averaging property implied the maximum principle. And hopefully you'll see that since u twiddle minus u is 0 on the boundary, it'll be less than or equal to 0 inside. And a classic trick is once you see that, then you repeat this argument for u minus u twiddle. So repeat with u minus u twiddle in place of u twiddle minus u. You'll get that u twiddle is identically equal to u, and this one, of course, is harmonic, so u twiddle is harmonic. So that's going to work. Okay, so let's see. This is the idea. Now here's the details. Let's see. U twiddle minus u is continuous on a compact set. D1 0 closure, so it assumes a max. its max. M. Well, it's 0 on the boundary. So maybe we want to see that the M is less than or equal to 0. So I want to see M is less than or equal to 0. Well, let's assume that M is bigger than 0. Okay. Remember, we know u twiddle minus u is equal to 0 on the circle. Okay, so let's say say, I guess I'll call capital U of z naught, which is u twiddle of z naught minus u of z naught, is that max. Okay, now for the picture. Here's the unit disk. Let's see, here's the z naught. The z naught can't be on the boundary because it's 0 there. So note, z naught is not in C1 of 0 because it's 0 there. And M is max is bigger than 0, we're assuming. So it's got to be inside somewhere. And now we know it satisfies the averaging property. And so all these little circles I could put in, it satisfies the averaging property. I can let those circles get bigger and bigger until they just internally tangent to the unit circle. So this is the unit circle here. And now I'll make a weird color here. How about magenta? Okay, if the averaging property holds on those black circles, then it would hold on this biggest one. Let's see, maybe I can make this thing turn green. Green circle. Yeah, so the averaging property holds on the black circles. I let them expand until I get to that green circle. And it would also hold on that green circle by uniform continuity. So important, the averaging property holds on the biggest circle there in the picture. In the picture right there. And you would use uniform continuity and limits. So we have uniform continuity on a compact set. I've kind of done this in the past, so I won't do it again. So use uniform continuity and take limits of as the curves expand, as the circles expand. Okay, and now you think about the averaging property on that green circle. Capital U is 0 right here. What should I call it? U of P is equal to 0. That point right there, P. And the average of that continuous function on the green circle is going to be M. And it's 0 right there. So that means it definitely gets less than M at some point. So we know that U is less than or equal to M on the, I should call that green circle something. What should I call it? C max. So U is less than or equal to M on C max. And 0 at P. Okay, and when you do the integration, M is u of z naught, and that's equal to 1 over 2 pi, the average. Oh, I should give that. It's the average of u on the green circle. And of course, that's less than or equal to m. So we are in that exact same situation of when we prove the remember the graph. Here's m. Here's 2 pi. That integral is as big as it can possibly be. And if it dips down to 0 right here, there's no way that integral can be as big, there's no way that integral can be equal to m. So since capital U of P is 0, that average must be less than m. Strictly less than m. And that's a contradiction. Okay. So m can't be positive. Okay, so we conclude that u twiddle minus u is less than or equal to 0, which, by the way, is equal to the max of u twiddle minus u on C10. It's kind of that's the maximum principle. That's why I called it that. Okay, so now there's the rest of the details. I can repeat the argument. Repeat using u minus u twiddle in place of u twiddle minus u. And then, of course, we get that u twiddle minus u is identically 0. And so u twiddle on the whole disk. Not just on the circle. So u twiddle is equal to u, and u we know is harmonic. So we're done. That's a beautiful argument. Questions about it? And a very similar trick is going to give us the Riemann removable singularity theorem for harmonic functions. Okay, so let's assume u is a real valued harmonic function. All my harmonic functions are real valued. Stein lets them be complex valued, which means it's u plus iv, where both u and v are harmonic. So we assume u is a real valued harmonic function on a punctured disk. So d r about z naught minus z naught that is bounded on a punctured disk like that. I guess I should say what I mean by bounded. Well, we'll see in the proof that it can be just bounded above. But usually bounded means the absolute value of u is less than something on there. Let's call this omega on the set. Then z naught is a removable singularity for the harmonic function, meaning we can give it a value there. Z naught is removable. Meaning we can give u a value at z naught that makes it harmonic on the whole set. To make it harmonic on the non-punctured disk. Okay, that's the theorem. And the proof's going to be a very similar thing to the previous thing with a sort of a clever twist to it. I guess before I give you the simple proof example, we can't reduce this to the old Riemann removable singularity theorem because of the example natural log of mod z. That's harmonic because it's locally the real part of a complex log function. You just take the branch cut going out the other side. And you see, oh, that's, yeah, locally it's given as the real part of a log complex log, so it's harmonic. And so that's harmonic on D10, and it blows, but it doesn't have a harmonic conjugate. So I can't, get an analytic function and use the standard Riemann removable singularity theorem.
Is it harmonic at the point 0?
No, it doesn't. It's minus infinity there. So it's not even defined there. So, but it's going to be an important piece of this proof. It has no harmonic conjugate. What did I say? No wonder. Sorry about that. It's harmonic on that. And there's no harmonic conjugate, so I can't reduce it to an analytic version of anything. And in fact, it goes to minus infinity. Well, in fact, we have log mod z is less than or equal to 0 on the closed unit disk minus the origin. And it blows down to minus infinity. And the limit as mod z goes to 0 of log mod z is minus infinity. So that's something to keep in mind. Okay, so the proof is going to, we can reduce our attention to the unit disk again. We can assume
I have a quick question.
Yeah.
wouldn't that just be harmonic on di0 removing the entire vertical line?
Vertical line? No, it's harmonic everywhere. So you're thinking of branch cuts? The principal branch of log removes the negative real axis.
Yeah,
And so that would show that that's harmonic except to the, on the negative real axis. But then you could take the different branch of log that goes out the positive real axis, and then you'd see it's harmonic on the negative real axis. So let's see. We can assume dr. We can assume we have our u is harmonic by doing the change of variables just like before. We can assume it's harmonic on d1 0 minus 0. And by shrinking the radius, if I want to a little bit, I can also assume it's harmonic on a bigger set. So let's see, I can assume it's harmonic on a slightly bigger radius than 0. Can assume it's harmonic on that. With r bigger than 1. And we can assume it's bounded by something. I'll make it only bounded above. And let's say absolute. Let's say that u is less than m on that set. Okay. Now I'm going to let u be the Poisson integral of the boundary values of that. What? I got to let it be a u twiddle. Let u twiddle be the Poisson integral of u of e to the I theta. On the unit circle. Okay, so that means that u twiddle equals u on the unit circle. Okay, here's a sneaky trick. I want to use the maximum principle. So this is a fiendishly clever sneaky trick. The best kind. I guess some people are offended by these sneaky tricks. Took a long time to think of this, probably. Let's define v equals u minus u twiddle. That's 0 on the unit circle. And plus epsilon times log of mod z. This thing is bounded. And this thing is harmonic. On the punctured disk on d1 0 minus 0. In fact, it's harmonic on a bigger one, and it's equal to 0 on the unit circle. And this thing is also equal to 0 on the unit circle. So fascinating thing. because that thing log mod z goes to minus infinity at 0, so does v. Okay, so let's see. Here's the aha. V is harmonic on the punctured disk. Let's see, we know U and log mod Z are harmonic on the punctured disk, and U twiddle is harmonic on the whole thing, because it's a Poisson integral. So V is harmonic on the punctured disk. That's number one. V is identically 0 on the unit circle. And the limit as z goes to 0 of v of z, as mod z goes to 0 v of z, is minus infinity in the real sense. So, if you think of an averaging property, let's think of a maximum principle. It's 0 on the outer boundary, and it goes to minus infinity at the puncture. If there's a maximum principle, it should be less than or equal to 0 in the whole thing, which should be a kind of an astounding thing, because you'd think it would depend on epsilon. And we'll see that it's not going to make any sense. So that feeling is correct. So the feeling is there must be a maximum principle. And there is one. There must be a maximum principle for this situation. And there is. Let's see what it is. I had a theorem about a maximum principle, but the function needed to be continuous up to the boundary to apply that maximum principle. And of course, that it's not continuous up to the puncture. And so the deal is, here's the big idea. I'm going to take, this is the unit disk right here. Then I'm going to punch out a little disk of size delta here. So that's going to have a little radius delta. This is going to be radius delta. And then I'm going to have a maximum principle on this shaded region. Okay. And I'm going to apply the maximum principle on that thing. But let's think about it. Since I got to think about that delta. Since v of z goes to minus infinity as mod z goes to 0, eventually it's less than minus 1. So there exists a delta such that delta is less than 1. Such that v of z is less than minus 1. Pick any negative number you want there instead of minus 1 when mod z is less than delta. And now if I want to apply the maximum, I want to see the pick a spot in here. Any old spot, z naught. So let's pick z naught in the annulus from delta to 1, about 0, in the picture there. I can assume yeah, that works. now I can now the maximum principal on that set on A delta 1. That function is continuous up to the bound, so the maximum would occur on the boundary. So it's maximum principal number 2, remember? Max occurs on the boundary. In fact, it's attained on the boundary. So that means that V of Z naught is less than or equal to the max. Well, on C1 it's 0. And on the other boundary it's minus 1. And so that means the V is less than or equal to, Z naught is less than or equal to 0. And inside this, the delta part, it's less than minus 1. V is less than minus 1 on the inside part, d delta 0 minus 0. So V is less than 0, less than or equal to 0 on the closed unit disk minus 0. And now, like I was saying, so I did use a maximum principle, and it's basically the standard one. You just had to poke a little hole and make a domain. If you poke the hole small enough, you're safe. That's a standard trick. Now the shocking thing is that that's a true statement for any old epsilon. So it should occur to you that, well, I can make that epsilon shrink away to nothing. We can let epsilon shrink down to 0. So we would have that V of Z is equal to, what was it? U minus U twiddle plus epsilon times log Z. We know that that's less than or equal to 0. And as I let epsilon go to 0, this part goes away. And so that leaves us with is that U of Z minus U twiddle of Z is less than or equal to 0. On that. And now I do the standard thing. I repeat the argument. Repeat using U twiddle minus U in place of U minus U twiddle. And we see that U is equal to U twiddle on the punctured disk. So, of course, I can make U harmonic by giving it the right value of U twiddle at the origin, which is the average. So it's removable. If we set U of Z equal to the average e to the I theta d theta, if we set it equal to that, U is harmonic on the whole disk. So it's a really clever, simple thing to do. Just uses the maximum principle.
I have a quick question.
Yeah.
So if I remember correctly, the only condition on U that we had was that it was bounded above. Wouldn't that
Right. So let's see. Where did I need it was bounded below? I'll tell you where. I needed to know.
Oh, did we have those bounded below?
I assumed it was bounded below. Yeah. So what should I say? Assume U is harmonic. Let's say that U. Why don't we say that? I need it's bounded because I need that green word bounded there because I want that function to go to minus infinity. I guess it would. Yeah. Yeah, let's just make it bounded. If you want to think hard about it, you can see that you'd get a maximum principle if it's a positive bound, and then you'd get a minimum principle if it's a negative bound, and you need both to.
Yeah, it kind of messes up with the symmetry when you swap U and U twiddle, essentially.
Yeah, so that's why I like a symmetry. Let's keep it a symmetry. Let's see. Thanks. Here's a fun fact that I've sort of been obsessed with over the years. If you look at my little paper on something about Poisson and Dirichlet, if the solution to the Dirichlet problem with, let's suppose, to the Dirichlet problem, on the unit disk with polynomial data. Boundary data. Is a harmonic polynomial. Kind of an interesting, fun fact. Let's see, what's the proof? The proof is easy. Let's suppose we have a real polynomial, p of xy. And that would be a polynomial of x is z plus z bar over 2, and y is z minus z bar over 2I. And that we could expand as a polynomial sum as nm goes from 0 to some order n. Complex numbers cnm z to the m, z bar to the m. And here's the easy way to see that I can extend that as a harmonic function. Z to the n times z to the m. Let's think of some cases here. If n is equal to m, that's equal to 1. So that would be equal to z to the 2n, which is equal to 1 on the unit circle if n equals m. Okay, and let's think about what it would do if n, let's make m the big one. I'm sorry, let's make n the big one. So what happens if n is bigger than m? By the way, 1 has a harmonic extension to the inside as 1. Okay. If n is the big one, then I would write it as z to the n, let's see, n minus m, because n is the big one, And then what I would have left with is z bar to the m times z to the m. And this is equal to 1 on the unit circle. So this is equal to z to the n minus m. That has harmonic extension as a u plus iv, where the u and the v are both harmonic. Okay. And then the last case would be if m is the big one. Then I would have, let's see which one. I want to get the z bar. Doggone it. There was a bar supposed to be there. Hopefully it'll make more sense. If m is the big one, then I would have a z bar to the m minus n. And here I would have a z to the n, z to the bar n. And this part is equal to 1 on the boundary. And so this is equal to z bar to the m minus n. And that's the conjugate of a harmonic thing. So I'm going to extend this one by 1. This case, I'm going to extend the boundary values to the inside by z to the n minus z to the n minus m. And this one, I'm going to extend z to the m minus n, z bar to the m minus n. Okay, when I do that extension, I will get an extension. Let's see, what's my extension? It's going to be a polynomial in z and z bar. So it's going to look like it'll be a get extension as a let's see, I get a q1 of z plus q2 of z bar, where these are polynomials with complex coefficients. These are polynomials. And of course, the solution to the Dirichlet problem would be the real part of that. And the real part of that thing would be a polynomial. The imaginary part actually turns out to be 0. And you can, because if I have a real valued p there, p of xy, then of course the solution to the Dirichlet problem would be real, and the v part would be 0 on the boundary, so the v would be a harmonic function that's 0. So it's going to be the real part of q1 of z plus q2 of z bar. And that's a polynomial. This thing is a polynomial in x and y. So it's a polynomial harmonic function. It turns out there's only one other domain that anybody's ever going to think of that has that property. And so ellipses satisfy this property too. How do you spell ellipses? Have the polynomial data to polynomial solution property too. And the famous Hobinson-Shapiro conjecture is that the disks and ellipses are the only domains that have the property. And that turns out to be an open question. Everybody believes it, but nobody